Right, so our last talk is from Laura Mikula, and she's going to talk to us about eye movements while driving. So yeah, take it away, Laura.
Okay, forgot to unmute myself. So today I'm going to talk to you about some work that I've been doing for the past year at the University of Montreal. And I'm going to talk about how we can use dynamic analysis of eye and head movement to estimate visual and cognitive demands while driving. So when we're driving, there's a complex interaction between vision and cognition. So for example, imagine yourself driving while you have your vision blurred, and you also have to multitask when you're in your car. Because our mental resources are limited, the inability to meet visual and cognitive needs can actually affect your driving behavior. It can have detrimental effects on road safety. Furthermore, it has been shown that eye and head movement contribute to attention allocation, and they can be modulated by the quality of vision and the cognitive load. So that's why in the study, our question was to see if eye and head movements were modulated and therefore be markers of increased visual and cognitive demands. So in order to do that, we had 21 young participants coming into our lab, and they were in a driving simulator, and they were doing quite a simple driving task where they were on a highway, and we asked them to maintain a speed of 90 kilometers per hour as accurately as possible. And I will refer to this as our single task because on some occasion on the GPS screen, some picture will appear with road signs, and we ask participants to report the number associated with the city of Montreal while still doing their driving task. So it's their double task that they have to do. So we used within subject design. So each of our 21 participants did 2 driving sessions. One session with optimal vision. So it means that we made sure that their vision was at least 20/20. And they also completed a second session where they had to wear contact lenses that are going to be perturbing their vision. And we measure that as a reduction in visual acuity. So we have half of the participants with a lower visual degradation, where the visual acuity is estimated to be 20/50. Whereas for the other half of the participants, they had a much higher degradation, where their visual acuity is estimated to be around there. In our participants, we also measured eye and head movement in 2 axes. So the yaw axis will be left to right rotations, and the pitch axis will be up and down rotations. So first off, I'm gonna present you the driving behavior of our participants to see how the driving was affected by the cognitive load and the visual degradation. So I'm presenting 2 driving parameters, which are the variability in the driving speed here and the variability in the car lateral position. So basically these 2 measures are going to tell us how the participants are stable in their speed and in their position relative to the middle of the road. So we ran a 3-way ANOVA, and we found that for both driving parameters, there was an effect of the cognitive load. So it means that in general, participants were more variable when they were doing the double task, as shown as triangles here, compared to when they were doing the single task. So when they had to just maintain their speed. Then for the driving speed, we found a main effect of the visual degradation, which means that participants were overall more variable in their speed when vision was degraded as compared to when vision was optimal. And then we didn't find any main effect of the experimental group, so no significant difference between the lower and the higher degradation groups in any of the driving parameters. So then we move on to look at some visual exploration parameters that are classically used in the literature. And here I'm showing you the gaze distribution in the vertical and in the horizontal axis. This is for all participants in the optimal vision condition and in the degraded vision condition. And as you can see here, there's not much of a difference between these two conditions. And this was further confirmed when we looked at the variability of the gaze position in the horizontal and in the vertical axis. There was no significant difference between the degraded condition compared to the optimal condition. And again, we didn't find any differences between the lower and the higher degradation groups. It was also similar for fixation duration, which is another parameter that is commonly used in previous studies. So it was quite surprising to us that we didn't find any differences. So we move on to some more dynamic analysis of eye and head movement. And to do that, you can use the entropy. So it's a measure that has been used in previous studies about driving, but also aviation. I won't go into the details of how it is calculated, but the thing to remember to know is that the entropy is going to estimate the randomness or the predictability in your eye movement scanning pattern. And generally with a higher entropy, you have more of an exploratory behavior. And when the entropy is low, it's generally associated with more stereotyped movements. So we calculated the eye entropy for every participant in both optimal and degraded vision condition. And we found an effect of the visual degradation. So the eye entropy was reduced when vision was degraded compared to when vision was optimal. But again, here we didn't find any differences between the two experimental groups. And finally, the last measure that I'm going to talk about is the eye-head coordination. And here I'm just presenting the results for the yaw rotation, so the movements in the horizontal axis. And here what you can see in these subplots is that we have the head in space rotation plotted as a function of the eye in head rotation. And we did that for both experimental groups and both optimal and degraded vision condition. So basically, when you're doing the regression between the head rotation and the eye rotation, it's going to tell you how much the head is contributing to gaze shifts. So if the slope of the linear regression is close to 0, it means that the head is not contributing much and only the eyes are contributing to your gaze shifts. However, if the slope is very close to -1, it means that your eye rotation is counteracted by your head rotation. So it means that if your eyes are 50 degrees towards the right, your head is going to be 50 degrees in the opposite direction. And as a result, your gaze will remain somewhere around 0, 0, so around the center. So we did the linear regression for each participant, and we compared the slopes. And the red line that you see here is the average slope of the linear regression. So we did in ANOVA, and we found that there was a significant main effect of the visual degradation, but no significant main effect, the main difference between the two groups. So basically, when the vision is degraded, the slopes are steeper and closer to -1. So it suggests that when vision is degraded, the head is contributing more to gaze shifts. So in conclusion, what we have shown is that the driving behavior and some of the most commonly used visual exploration parameters were rather insensitive to our particular visual degradation. But in contrast, the dynamic visual exploration and the Ihead coordination were somewhat impacted by the visual degradation in this condition where the cognitive load is high. So it suggests that the dynamic analysis of eye and head movement could be used as indicator to estimate visual cognitive demands during more naturalistic tasks, just like driving. And with that, I would like to thank you all for your attention, and I'm happy to take some questions.
That's great. Thank you, Laura. I feel like this throws up a ton of questions. The first one that occurs to me, is this something that could be used by like policymakers to set what the rules should be for what devices you're allowed in cars, or is it not quite well enough developed yet to be at that stage?
It's difficult to do right now, but yeah, the idea with this study was also to see if we can see when like to see the visual scanning pattern of the participants and kind of try to extract when maybe it could be dangerous.
Yeah.
Yeah, but it's not at the point where it can be used right now.
Right. Yeah, as I was watching, I was thinking there's a load of like things that you could start testing with this, like certain types of devices or certain positions that you put devices more distracting or not than others, and all sorts of things. If you had a good measure that correlated with, I guess, how safe people's driving were and things like that.
Yeah, because the thing is, when you're using in-vehicle displays, it can actually have an impact on your cognitive resources. So you have less cognitive resources to process the visual scene and the road. So yeah, that was the idea here.
Okay, actually, loads of questions have come in, so I'm going to stop asking my questions and start asking some from the audience. Okay, so we have so Laura, great talk and excellent visualizations. I'm curious, which gaze tracker did you use to obtain both eye and head movements?
The eye tracker that we used was a portable one. So you have kind of some glasses without the lenses that the participants are putting. So it's going to record your eye movements. And we also have kind of a headset that participants are wearing, and they have some reflective markers. So it's going to track the markers just like you will do when you're doing motion capture with hand movements, for example. So we kind of combine these two techniques, and we're doing some calibration for the head movement, the eye movement, so that we can have a recording for the eye, for the head, and then we can reconstruct also the gaze rotation in the space.
Cool. There was a follow-up second question to that, which was, did you perform any temporal analyses close to when the stimulus appeared on the GPS?
We didn't do that. Actually, a thing that I didn't mention is that generally the entropy that I presented, it's more spatial based. So basically you will divide your visual scene into some region of interest, and you will look at the visual scanning pattern. But here we didn't want to be dependent on the visual scene because it's going to change a lot with just when you're driving. So with the entropy that I presented here, we looked at the entropy over time.
Cool. Okay. I think we have to finish there because I think we're going to get cut off in like 1 minute. So I better quickly wrap up and say thank you again, Laura, and thank you to all the speakers in the sessions. I certainly learned a ton about